You guys actually already know Niels Bohr's greatest contributions to our understanding of the atom, and you have actually probably been familiarized with it for several years. Possibly as far back as grade school, you've probably been working with this. So Niels Bohr builds on the understanding that Rutherford and Thomson gave us, and he created his own model of the atom, or what he thought the atom looked like. And it looked like a lot like that. Where have you seen that before? Jimmy Neutron, Big Bang Theory. Okay, so it's a very, very common symbol. And in fact, it's so well used that even though it's not exactly correct, it's stuck around a lot and is very prevalent in pop culture because it's easily recognizable as being a model of the atom. So this is the most common representation of an atom in pop culture. Representation of an atom in pop culture. And part of the reason it's so common is that compared to some of those other people we talked about, it's relatively new. Niels Bohr produced this in around 1913. So yeah, it sounds like a long time ago, 100 years. Well, some of your grandparents may be 100 years old. Or at least my grandparents are nearly 100 years old. So great-grandparents, is that probably better? Closer? Okay. Great-grandparents are about 100 years old. And some of the different parts of the atom that he builds with here are, first of all, that in the center, that's where we're going to find the nucleus. The same piece that Rutherford identified. And Bohr recognizes this is where protons and neutrons would be. So protons and neutrons exist in the nucleus. Okay. He then identifies that the electrons actually exist in orbits around the nucleus. And he says that the electrons orbit in the same way that planets orbit the sun. Electrons orbit the nucleus like planets orbit the sun. And furthermore, he found that certain electrons have more energy than other ones. So certain orbits have more energy than other orbits. Have more energy than others. So we worked with this understanding of the atom for actually a very short amount of time before we figured out that actually there's a better version and a better understanding to be had. And this version lasted probably only about 20 to 30 years. So as we roll into the 1930s and 1940s, we started to put together the modern model of the atom. Modern model. And today in the project that you're going to get, you're going to be able to research a couple of the individuals who helped put together the modern model of the atom to find out a little bit about what was their contribution. So the big thing for the modern model, even though the nucleus looks basically exactly the same as in the Bohr model, the electrons are in completely different arrangements. First of all, rather than these nice orbits that Bohr gave them, the modern model of the atom says that they're kind of in a cloud and they move randomly in certain zones. So electrons are located in an electron cloud, which is a zone around the nucleus, which is a zone around the nucleus. So Bohr was kind of right when he said certain orbits have more energy than others. Only they weren't really orbits. So we kept the idea, but we changed it to be energy levels. And an energy level is basically a smaller zone in which an electron can be found. If you think about an apartment building or a hotel, energy levels are kind of like the floors to the apartment building or hotel. So these are smaller zones. An electron, and I'm going to use E with a negative sign for electron because I'm lazy. What's the charge of an electron? Negative, so that should make sense. Okay, smaller zones, an electron with specific energies can be found in. And as electrons are given more energy, so maybe they're hit with something, maybe a certain color of light is shined on them, but if you give an electron more energy, it can jump up to a higher energy level, or even leave the atom entirely. So it can jump up to a higher floor on your apartment building. So with additional energy, electrons can go to higher energy levels or leave the atom completely. Electrons can move to higher energy levels or leave the atom completely. What is created when we get rid of an electron from a neutral atom? When we get rid of an electron, what does it turn the atom into? From yesterday's assignment. From yesterday's assignment, if you take away an electron, what happens? You don't lose mass and it doesn't change the element. Charge. What happens to the charge? Goes up or becomes positive. So what was the term that it used, the assignment used for a positive atom? Ion. There we go. So if we were to get rid of an electron entirely, we would create a positive ion. Okay? So energy levels, they're basically like floors to an apartment building. I'm going to put that in here, floors, where you can find atoms of different, or sorry, not atoms, electrons of different energies. As you go up to higher energy levels, you have higher energy electrons. All right, so just like an apartment building or a hotel is subdivided into floors, how is each floor subdivided? Rooms. And we call those rooms for the atom orbitals. All right, we just said that electrons don't actually orbit. Anybody got a guess as to why we would call these orbitals? Some of them are. Other thoughts? Why might we call them orbitals? No. So, it doesn't actually have anything to do with how the electrons move. The reason we call them orbitals is because we're looking at Niels Bohr, who said that electrons move in orbits, and we're giving him a nod and saying that was a good idea, but you were wrong. So we're giving props to Niels Bohr in that he came up with this good idea for orbitals, and we use his atom model on everything. So we decided to stick with the word, and it has absolutely nothing to do with the way electrons actually move. So orbitals are like rooms on the individual floors, and they're basically subdivisions of energy levels. subdivisions of energy levels. And orbitals come in 4 different types. Orbitals come in 4 types. And these are basically random letters. S, P, D, F. I'm just going to make a quick chart here. So, a few details about each of these types of orbitals. The s orbital is spherical in shape, so Colin was close there. So, sphere. The p orbital is shaped kind of like a peanut. And the d and f orbitals are super complex, and we aren't going to worry about their shape. Okay? So yesterday, you guys worked with the simulation, and it actually showed different energy levels for the electrons. And it showed that by showing different circles. How many electrons could you fit on that first circle before it made you move them to an outer circle? 2. The reason there are only 2 electrons on that first circle is because the first energy level only holds 2 electrons, and they are held in an s orbital. So this holds 2 electrons. The p orbital can hold up to 6 electrons, the d holds 10 electrons, and the f holds 14 electrons. Did anybody notice how many electrons can be held on the second ring around that simulation? It wasn't. No, it was way less. It was 8. You could hold 8 electrons in that second energy level. So if I can hold 8 electrons in the second energy level, what kind of orbitals do you think might be there? An s and a p. Because we need to hold 2 and another 6 to get 8. Anybody want to guess at how many electrons could fit on your third energy level? Why 18? Yeah, you added an S and a P and a D. Who wants to take a guess at how many can fit on the fourth energy level? Who said 32? Good. 32 is right, because on the fourth energy level, you get 1 of each, and so on and so forth. After the fourth energy level, there are more energy levels. There's 6, 7, and 8, but they just continue to have these orbitals. There's no extra ones later. Okay, so the first energy level holds the lowest energy electrons, and it can hold 2. The second energy level holds the next lowest energy, and it can hold 8. The next lowest energy level 3, can hold 18. And the last of those energy levels that we're going to worry about, energy level 4, can hold a total of 32. Okay? So electrons can move between them by gaining or losing energy. But really otherwise, all we need to know is that there's zones for an electron to be found in as they kind of move randomly through them. Questions about orbitals or energy levels or the modern model of the atom? Yeah?
Okay, so if it's going like 2, 4, 8, yeah, whatever, why did we write down 2, 6, 10, 14?
It doesn't go 2, 4, 8. It went 2, 8, 18. So 2, sum of 6 and 2. What's the total?
Or, 8, sorry. I thought we
So
were adding
2, 8, what's the next total?
of what? Oh, okay, I got it now.
18, 32. Good? Okay. Anybody else? Other questions? Okay. So that covers all we need to